Well, hello, good people. Today we are talking about Newton's second law. Now we are going to start our discussion of Newton's second law with Newton's second law. Here's what Newton's second law says. Newton's second law says that the acceleration of an object is directly proportional to the net force acting on that object divided by the mass of that object. Now, when we look at Newton's second law, first things first, I'm going to go ahead and put that equation in a box. From this point forward, anytime when I put an equation in a box, that means that you can add that equation to your bag of tricks. It's an equation that is worthy of being remembered, memorized, and kept in a very special location on a very special bag of tricks piece of paper that you will keep with you for the rest of the whole school year. So do put that in a box to write that equation down. It is essential to know that A is equal to F net over M. Now, let's talk a little bit here about what each of these symbols means. A is acceleration, F is a force, and M is a mass. Most students know Newton's second law as F net equals ma, or force equals mass times acceleration. I will also allow this version of the equation as an original version of the equation. However, I always start with this version of the equation, and this version of the equation is my standard for what is the original equation. There are two reasons why I use this equation and I don't use this equation as much. One of the reasons why I use this equation is because this is the version of the equation that all the people are using nowadays. It is all the rage. The AP Physics equation sheet does not have F net equals ma on it. It has A equals F net over M on it. And the reason why it has this, and this is the second reason why I use it, is not just because it's more popular and all the rage, but it's because there's a physical reason for that. The reason why we use this equation instead of this equation, generally, is because this equation does a much better job of showing the dependent and the independent variables. Here's what this equation shows. This equation shows that for a certain force and a certain mass, there is a certain acceleration. In other words, it shows that the acceleration that an object experiences depends on the force that that object experiences divided by the mass that that object has. This equation makes it look like force depends on mass times acceleration, which is not true. For example, if I were accelerating in my car, I would not say, oh, hey, would you look at that? I am accelerating a lot. That must mean that because I am accelerating a lot, I am making a very big force on me. That does not make any sense. What we would say instead is there's a very big force on me. That must mean that that very big force on me is making me accelerate a lot. Do you see how acceleration depends on force? Force does not depend on acceleration. An acceleration does not create a force creates an acceleration. So with this equation, you have the dependent variable over here and all the independent variables over here. With this equation, they're all kind of mixed together. So this equation is my preferred version of the equation, but either one works. Let's start by talking a little bit about why this equation makes sense to us as people who live in the world and as people who know a little something about inertia. The reason why this equation makes sense to us as people who live in the world is because we know that the bigger your force, the bigger your acceleration. All kids know Newton's second law, especially kids who like swings. Because any kid who has ever been pushed on a swing before will tell you, push me with a bigger push, because here's what they know, is that a bigger force, a bigger push, leads to a greater acceleration, and they know that the more that you push them, the faster they will go, the greater their change in velocity will be. So all kids know that force and acceleration are what we call directly proportional, that as the force goes up, the acceleration also increases. Next, it should make sense to us as people who know about inertia, that acceleration is inversely proportional to the mass, that as the mass increases, the acceleration decreases. This is because the more mass that an object has, the more inertia that it has, which means the more tendency it has to keep on doing what it's doing. And so if it has more mass, it has more inertia, and it has a greater tendency to continue on in its state. It would take more force to accelerate something that has more mass. And so the amount of acceleration does depend on the amount of mass. The same amount of force would accelerate a Toyota Camry much less than it would accelerate a semi-truck. So there's the kind of conceptual understanding behind Newton's second law. Let's take a look here at our units. You know that the units of mass are kilograms. You know that the units of acceleration are meters per second squared. Now, if you wanted to do a little bit of dimensional analysis, you could find the units of force. To find the units of force, let's look over here. Mass is kilograms. Acceleration is meters per second squared. In order for this to be a viable equation, then the units of force have to be kilograms times meters divided by seconds squared. And these are the units of force. The units of force are kilograms meters per second squared. Although all of the good physicists of the world who used to say kilograms meters per second squared, kilograms meters per second squared, kilograms meters per second squared, got very, very tired of saying kilograms meters per second squared, because really it truly is a mouthful to say kilograms meters per second squared every single time you want to talk about a force that has units of kilograms meters per second squared. So all of the good physicists of the world said, let's stop saying kilograms meters per second squared, and please, is there anything shorter? And they said, yes, we shall call a kilogram meter per second squared 1 Newton. And we represent newtons with the capital letter N. Represent newtons with the capital letter N. Newtons are, of course, named after Mr. Isaac Newton and named after Newton's second law, so it makes sense that we use the units of newtons for force. It does have to be a capital letter N. It cannot be a lowercase letter n, because that means something totally different in physics, so please make sure that you pay attention to your capitals and your lowercases. Okay. That's a little bit on what Newton's second law is. From this point forward, we will now discuss two new topics based on Newton's second law. The first one will be this concept that we call net force. And as we discuss net force, we'll also discuss the concept of equilibrium. And the second concept that we are going to talk about, which is going to be an application of Newton's second law, is the concept of weight. So we will start today by talking about net force and equilibrium. Then after that, we'll end our video talking about weight, and those will be our two topics which kind of consume the rest of what we talk about today. Let's start by talking about net force and equilibrium. Take a look here at this equation. Do you see in this equation this little summation symbol here? That summation symbol means add them all together. And that summation symbol means that we are talking about the net force or the total force. This summation symbol you're going to see is very, very significant, and let's take a look as to why. Let me pull up another picture here. Suppose that I had, wait 1 second. Sorry, it can do it. You got it, buddy? Yes. Load, you can do it. Yes, okay. Here we go. The new drawing is coming to you at some time very soon. Okay, suppose this, while this is getting loaded. Suppose that I have a book and that I set this book down on my desk, just like this. Wait, let me make it bigger. Okay, suppose that I have a book sitting on a table just like this. If I have a book sitting on a table just like this, well, you would say that the acceleration of this book is 0 meters per second squared, because it doesn't really seem to be going anywhere. But then if I asked you, is there a force on this book? Well, you would say, yes, there is at least one force on this book. Now this, if we did not have that little net symbol in front of that equation that we have for Newton's second law, this would be very, very confusing, because it says that A is equal to F over M, and there is F, but there is M, so that would be two numbers, but there is no acceleration. So you can't have something divided by something equals 0. That's not possible. This is where the summation symbol is very, very important. And this is also where our vector hats are very, very important. We have to consider the net force. Let's take a look at a picture here. Okay. Let's take a look at a picture. Here is my book sitting on a table. Oh gosh. Oh my. Okay, let's try this again. Make sure we're all lined up here. Here is a, well, that's just not. Okay, that's okay, fine. It's fine. Here is a book sitting on a table. If I asked you what forces are acting on this, well, you say, well, one force, Miss Wilson, would be gravity. Gravity is pulling down on the book, and I would absolutely agree with you that gravity is pulling down on the book. And I would also say that the table, oh my, let's draw straight lines. Okay, I would also say that the table is pushing up on the book. So gravity pulls down on the book and the table pushes up on the book. Now, if I wanted to find the net force, notice we got a vector hat here, which means direction matters. I got to define which way the net force is going. Which way is positive and which way is negative. Here's what I would say for this example, I'm going to call up positive and down negative, although you could flip those if you want to. I'm going to write them as up as positive and down as negative. So here's what I would say. I would say that the net force here is equal to the, I'm going to do this later. The force of the table plus the force of gravity acting on the book added together. Notice I put vector hats on these guys. Let's say that the force of gravity acting on the book is 12 newtons. And let's say that the force of the table, in this case acting on the book, don't you agree, would also be 12 newtons. So we would write it this way. We'll talk about why these are equal to each other in the future. But we would write it this way. We would say that the force of the table is positive 12 newtons because it's up, and the force of gravity is negative 12 newtons because it's down. And this means that the total force acting on the book would be 0 newtons. Now this here corresponds to Newton's second law, because we say that the total force, we have an up force that's canceled out by a down force. The total force acting on the book is 0 newtons, and so the acceleration of the book is 0 meters per second squared, because a total of none force is acting on the book. Now, we could write it this way, and this is one way to show adding net forces together. I want to show you another way to add net forces together so that you can see that there are really two different ways to account for our direction here. So here's one way to do it. It's just like this. Here's another way to account for direction. You can either do it like this with vector hats at the top, or you could do it this way. I could say that the net force, and instead of doing vector hats here, I'm going to do positive and negative signs in the front. So I could say that the net force is positive the force of the table, because I say that the force of the table is pushing up, minus the weight or the force of gravity pulling down on the book, which is acting downwards. Then when I plug in numbers, I already took care of my directions here, so I plug them in without any without any direction here. I just carry my positive and negative signs like this, and then I get a total of 0 newtons. Here's the difference. You can either start with vector hats and start with everything positive, then when you plug in numbers, you plug in your positives and negatives, or you could start by positives and negatives here instead of vector hats, then just plug in numbers instead of numbers with direction here, and you get to a final answer. Either one of these are okay, and either one would receive total and full credit on a test. I discuss it now because we're going to be writing net force equations a lot, and so it's good to see that there are two different ways to do it. Either way is totally awesome and totally great with me. Okay. So there we have our two different ways to write our net force equations. This book, we would say, is in a very, very special state. Because the net force is acting on this book is 0, and because its acceleration is equal to 0, we say that this book is in a state that we call equilibrium. In physics class, equilibrium means that the net force acting on the object is 0, and hence, according to Newton's second law, that the acceleration acting on the book is 0. This book is in a state of equilibrium because it is stationary. It is not accelerating, and the net force is equal to 0. Let's take a look at another example. Here is a true story about my life, is that when I went to Devlin Junior Senior High, every single day I would drive 20 to 25 minutes to get home from school. And when I drove 20 to 25 minutes to get home from school, those 20 to 25 minutes were spent, the entirety of them, all on Kipling, driving straight. It was a very boring drive to just drive straight on Kipling for 20 to 25 minutes. And so I came up with little ways to entertain myself. And one of these ways to entertain myself was to use a game that I like to call the equilibrium game. Here's the equilibrium game. The equilibrium game, the whole purpose of it was to keep my car in a state of equilibrium for as much of the drive home as I possibly could. If I wanted to keep my car in a state of equilibrium, here's my windshield, here's my front lights, here's my tail lights, here's my back window. Okay, well, now it's really hard. Let's say that it's going this way. We're moving this way. If I want to keep my car in a state of equilibrium, do you agree that there are two ways to do it? One way to keep your car in a state of equilibrium is to have it not moving at all and to have your car perfectly stationary. If your car is perfectly stationary and not moving, then we would say it is in a state of equilibrium and it's not accelerating. But that's not the only way to be in a state of equilibrium. The other way to be in a state of equilibrium is to have your acceleration be 0, which that could mean that you are either not moving nice and stationary or that you have a constant velocity. Here's how I played the equilibrium game in my car. My goal was to keep my car going at a constant velocity. If I could keep my car going at a constant velocity, that would mean that the net force on my car would have to equal 0. Now, there are a lot of forces that are happening on my car at any given point in my drive. First, gravity is pulling down. Now, on the flat parts of the road, I don't have to worry about gravity too much because gravity pulls straight down, but the force of the road would push straight back up, and it would counteract the force of gravity. Pretend that I drew that line straight down. The force of the road would counteract the force of gravity, and so it would push up. The gravity would push down. Does that say road? Can you even read that? Not really, but you get the idea. Okay, and so I wouldn't have to worry too much about that. What I would have to worry about, though, is that as I was moving forward, there would be other forces pushing back, like the force of friction, for example, or the force of air resistance, for example. And so here was my goal. My goal in my car, in order to keep my car in a state of equilibrium, is I had to press down the gas pedal so that my forward force, I'll say from my engine, the force from my engine, I don't know if you can hear, but they're playing a nice Cell song in the classroom next door. So if you can hear background music just kind of bumping along and it sounds sciencey, it's because it totally is. Okay, so here I have the force of friction here, and I have the force of air resistance here. My force from my engine has to equal the force of air resistance together added with the force of friction. So what I would do is I would adjust my foot on the gas pedal in order to keep the force from the engine exactly equal to the force of friction and the force of air resistance. And this is quite the fun challenge to play the equilibrium game. The only rule of the equilibrium game is you can only play it with green lights. Stay safe out there, people. One last equilibrium example, and then we'll talk about weight. Suppose this. Oh, and there's a bell. Suppose this. I'll draw a picture for you here. Once upon a time, there was a young girl by the name of Sally, and Sally wanted to be a circus performer more than anything else. It was her greatest dream. And so her parents, being very supportive of her dreams, purchased for Sally a trapeze bar, and they hung it up in the basement of their house. Now, and you ask why the basement? Well, that's because, like, if it were in the living room, then you would just have a trapeze bar sitting in the living room, which is not great decor. And as you know, all of the children's toys always go in the basement because that's where they can be out of the way, so that all the adults can hang out upstairs without any of the toys in the way. And then all the kid stuff is down in the basement where it can be kind of like tucked into corners and things like that. So anyway, so Sally's parents bought her a trapeze bar. They hung it up in the basement. And now they said to Sally, Sally, if you really want to be in the circus someday, you're really going to have to put in the hours. Like, you're seriously going to have to practice. And Sally said, yes, I absolutely understand. And so every day when Sally would come home from school, Sally would run down to the basement, and she would grab a hold of the trapeze bar like this, and Sally would hang from the trapeze bar just like so. Sorry, let me draw her sleeves. And then her dress. And there is Sally. Of course, she has curly hair. And there she is, looking amazing. Okay, now here's what happens when Sally hangs from the trapeze bar. First, there is a force that is pulling down on her. Wait, I kind of want to redraw this with my other color. First, there is a force that is pulling down on her, and that force is gravity. The whole world is pulling down on Sally. But then Sally is being supported by these ropes. She's also being supported by the trapeze bar, but Sally and the trapeze bar are both being held up by these ropes here. And these ropes each have a tension force in it. And when we talk about the tension force in a rope, what we are really talking about is how hard that rope is pulling on an object. So you have a certain force of tension in rope 1, and then you have also a force of tension in rope 2. Now suppose that Sally has is experiencing a force due to gravity, which is her weight. Suppose that she has a weight of 200 newtons. If she's hanging perfectly in the center of the bar, can you think about it for a second? Write it down in your notes. I got 2 questions for you. First, which one would be greater? Ft1, the force of tension in the first rope, or Ft2, the force of tension in the second rope? And second, what would each one equal? What would the force of tension in the first rope equal, and what would the force of tension in the second rope equal? Okay, here's what you should be saying. The first thing that you should be saying is you should be saying, okay, well, Miss Wilson, if Sally is being held up equally by rope 1 and rope 2 because she's sitting right in the middle here, if she's hanging right in the middle, well, then the force of tension in this side will equal the force of tension in this side, and her weight will be evenly distributed. Then you're saying, Miss Wilson, I know that she is in a state of equilibrium because she is not accelerating. So if her acceleration is equal to 0, her net force must also equal 0. And then here's what you're saying. You're saying that means that the up forces have to cancel out the down forces. So that means that the force of tension in the first rope has to equal 100 newtons. And the force of tension in the second rope has to equal 100 newtons. So that Sally's weight is perfectly evenly distributed between the first rope and the second rope. The net force is equal to 0. The net force is equal to 0 because 100 plus 100 up equals 200 down, and altogether that adds to equal 0. Now suppose this. Suppose that Sally scooched over to the side just slightly so that now she was slightly closer to rope 2 than she was to rope 1. Now, which one has more tension in it, rope 1 or rope 2? You should say rope 2 has more tension in it now because now Sally is closer to rope 2, and so rope 2 has to support more of her weight than rope 1 does. And that is absolutely true. Rope 2 would be holding up more of Sally's weight than rope 1. And now, here's another question for you. If, as Sally scooched slightly over this way, and F2 was pulling up with 150 newtons, how much would rope 1 be pulling up with? You should say 50 newtons, Miss Wilson, because these two together always have to add to cancel out that 200 newtons in order to keep Sally in a state of equilibrium. Suppose you go down into the basement and Sally is completely and totally all the way under rope 2 with no outstretched hands. Both of her hands are just directly under rope 2. What would be the tension in rope 2 and what would be the tension in rope 1? Well, you should say at that point, Miss Wilson, rope 2 is holding up all of her weight, and so the tension in rope 2 would be 200 newtons. And the tension in rope 1 would be 0 newtons. And isn't that true? If you went down into the basement while Sally is hanging all the way under rope 2, wouldn't you be able to twang this rope just like a guitar string? Wouldn't it have a lot of tension in it? But this rope over here, can you imagine it? Can you picture it in your head? Sally scooches all the way to this way. This rope has a ton of tension in it, and isn't this rope just kind of hanging a little loosey-goosey over there? Not a lot of tension there at all. In fact, none tension there at all. This, you can see, is an equilibrium problem because the net force always has to equal 0. Sally could shift her weight over side to side so that one rope has more tension in it than the other, but in total, these tensions have to add to cancel out her weight in order to have a net force equal to 0. Okay, and that brings us to our next and final topic of today, which is the topic of weight. And let's talk purple. Okay. Weight is defined as the force on an object due to gravity. That's what weight is. Weight is the force on an object due to gravity. It's the force on an object due to gravity. Weight is the force on an object due to gravity. Please underline in your notes where you wrote the word force. Weight is the force on an object due to gravity. Here is one of the biggest misconceptions of all time in physics class. So I'm going to give you like the biggest misconception. We're going to talk about it right now. Biggest misconception in first semester physics. Are you ready? Mass and weight are not the same thing. Your mass is not your weight, and your weight is not your mass. In your notes, please write this down somewhere. Please write it in bold letters, italicize it, underline it, all of those kinds of things. I shall put exclamation points on both sides to emphasize the fact that mass is not the same thing as weight. These are not the same. Mass is a measure of how much matter is in an object. Weight is a measure of how hard gravity is pulling on that object. Mass is how much matter is in an object. Weight is how hard the force of gravity is acting on an object. Mass is how much matter something has. Weight is a force. Check it out. We use the lowercase letter m to represent mass. You already know that that's old news to you. For weight, we use F sub g. We will never use the capital letter W to represent weight in this class, and there are two reasons for that. The first reason is because capital letter W already means something else in physics. It means work, which you'll see in Unit 4. That capital W means work, and so then that would be very confusing if work and weight were both represented by the capital letter W, especially because we use both of them at the same times often. The second reason why we use FG is because that reminds students what weight actually is. Weight is actually a force due to gravity. And so when students write down FG for weight, they remember that weight is a force. Weight is a force. Okay, let's try a series of questions. First, suppose that I had a mass that was 1 kilogram big. Here's a mass that is 1 kilogram. How much mass would this mass have on the earth? You say 1 kilogram, Miss Wilson. Isn't that its mass? And I would say yes, and mass is 1 kilogram. A mass of 1 kilogram has a mass of 1 kilogram. How much would a 1 kilogram mass on the moon? You say 1 kilogram. How much would a 1 kilogram mass on the sun? 1 kilogram. How much would a 1 kilogram mass in outer space? Still 1 kilogram. How much stuff is in a mass, or how much stuff is in an object, how much matter is in an object? That does not vary with location. So the mass of this mass here is always 1 kilogram no matter where it is. That is not the case with the weight. On Earth, 1 kilogram weighs about 10 newtons. So its mass is 1 kilogram. Its weight, sorry, I don't know why I'm drawing another mass because I don't actually need another one. Its weight on Earth is about 10 newtons. What would its weight be on the moon? More than 10 newtons, less than 10 newtons, or the same as 10 newtons? You should be saying less, Miss Wilson, because the moon would pull less hard on the kilogram on the moon than it would on Earth. What would its weight be like on the sun? More than 10 newtons, less than 10 newtons, or the same as 10 newtons? And you say More than 10 newtons, Miss Wilson, because the sun pulls harder on the 1 kilogram than the Earth pulls on the 1 kilogram. What would be its weight in deep outer space, far away from massive objects? More than 10 newtons, less than 10 newtons, or equal to 10 newtons. You say less than 10 newtons, Miss Wilson. In fact, it would be 0, because if you're in deep space and there is nothing to pull on the mass, then it has no weight, because weight is the force that it is experiencing. Weight is the force that something experiences. It is not the amount of mass in the object. Those are two different things. Here's a question for you. If your car ran out of gas and you had to push your car to the nearest gas station and you were on Earth, that would be quite a challenging day. If your car ran out of gas and you were on the moon, that would also be quite a challenging day. Here's a question for you. Where would it be harder to push your car to the nearest gas station? On the Earth or on the moon? Ignoring the fact that there are no gas stations on the moon, and also ignoring the fact that there's more air resistance on Earth. Where would it be harder to push your car? Think about it for a second. Take a moment. You should say, in this case, same. It would be equally hard to push your car to a gas station on the moon as it would be to push your car to a gas station on the Earth, ignoring the fact that there are no gas stations on the moon. Here's why. When you are pushing your car, let's draw a picture here for funsies. When you are pushing your car, wow, this is not a good picture, but that is a-okay. True story, by the way, I have been drawing cars the same way since I was in 3rd grade. Okay, if you were pushing your car on the Earth, then what you are trying to accomplish is you are trying to accomplish an acceleration of your car. And that acceleration would require you to give it a certain push over the mass. If you want the same acceleration on the Earth as on the moon, we can rearrange this to see how much force you would need. Well, that's not a very good F. We could rearrange this equation to see how much force would be required to get this job done. The force would be equal to the mass times the acceleration that you're trying to achieve. Now, if I'm trying to push this car forward on the Earth with a certain acceleration, then I care about how much mass it has, how much m it has. Now, if I'm on the moon, then I care about how much mass it has. Notice what I don't care about. I don't care about how much the car weighs. What I care about is how much it inertias. Because if it has more inertia, it's harder to push. But doesn't it have the same amount of inertia on the Earth as it does on the moon? Because the mass of the car stays the same. So it would take the same amount of force to push your car on the Earth as it would to push your car on the moon. Here's where it would be different though. It would be much easier to lift your car on the moon than it would be to lift your car on the Earth. Because if you're lifting your car on the moon, you have to overcome the weight of the car in order to lift your car. And if you're on the moon, the weight of the car is way less. So lifting it would require way less force. If you're on the Earth, the weight is more, so lifting it would require more force. So it would be harder to lift your car on the Earth than on the moon. But it would be the same amount of difficulty to push your car on the Earth than on the moon. This is a tricky question that really gets at the nuances between mass and weight. They are not the same thing. They are not the same thing. Okay, now the next thing that we're going to do here is we're going to talk about how to calculate weight if you know the mass of an object. Mass and weight are not the same thing, but it turns out that your weight does depend on your mass. Let's go ahead and take a look at an example here using the example of an elephant. Suppose let's do a little purple elephant like this. Suppose that you wanted to know the weight of this elephant here. Okay, yes. Sorry, this is a quick pause in the video for artistry and brilliance. I mean, come on, this is looking pretty good. You can't deny it. That's a pretty good looking elephant there. And add the tusks. And yeah, that's a pretty good elephant. If I wanted to know the weight of the elephant, well, I could use Newton's second law, because the weight is just the force due to gravity. And so I could rearrange A equals F net over M to say that F net is equal to mass times acceleration of the elephant, where M is the mass of the elephant and A is the acceleration of the elephant. Now, all that I would have to do is I would have to make F net the weight, which is the force due to gravity. That means that I need the only force so that it can be the net force. The only force on this elephant has to be the weight of the elephant. If the only force on the elephant is the weight of the elephant, then the net force on the elephant is the weight of the elephant. If the only force on the elephant is gravity, is its weight, then we would say that this elephant is in a state of free fall. And you already know, what is the acceleration of an object in free fall? The acceleration of an object in free fall is g. It's 9.81 meters per second squared. And so here is what we would get, is we would get an equation for weight that is always this equation. And yes, you can add this equation to your bag of tricks. We calculate the weight of an object by multiplying its mass times the acceleration due to gravity wherever that object is. So on Earth, the weight of an elephant is the mass of an elephant times its acceleration due to gravity on Earth, which is 9.81 meters per second squared. This is a calculation for the force, for the weight of an object. The weight of an object because of the force on an object due to gravity. The weight of an object. Now, let's do a quick practice problem. Remember, I'm trying to think of where to do my practice problem. We'll do it over here and then I'll erase it. Hey, do you remember my 1 kilogram mass from earlier? My 1 kilogram mass has a mass of 1 kilogram. What is the weight of my 1 kilogram mass on Earth? Well, you would say, Miss Wilson, that's easy. It's 1 kilogram times 9.81 meters per second squared. And its weight on Earth would be 9.81 newtons. Try this one. Suppose that I had a mass that this time was equal to 500 grams. If I have a 500 gram mass, how much does it weigh? Well, first, I got grams here, so I got to convert those into kilograms. I move my decimal place over 1, 2, 3, and I get that the mass of this guy here is 0.500. We'll keep 3 sig figs here. 0.500 kilograms. If I asked you to find the weight of this guy, you would say, no problem. The weight of this guy is 0.500 kilograms times g, the acceleration due to gravity, which is 9.81 meters per second squared. And you could do 0.5, that's basically means cut 9.81 meters per second squared in half, and you would get approximately 4.9 newtons. Sorry, I only kept 2 sig figs there, but I think it's 4.91 newtons, but you should probably check me on that. This is how you calculate weight. You take the mass of the object and you multiply it by its acceleration due to gravity. Notice that as we change planets, your weight changes, not because your mass changes, but because your acceleration due to gravity changes sizes. Now, one last thing before we go here. I'm going to erase the car, so sorry. Bye, car that was on the moon. That's so cool of that car to have been to the moon. That's super awesome. I've never been to the moon, but that car has been to the moon, which is really very cool for that car. Okay, here is the last little tidbit of information for you for today. And then, oh, why is my eraser not just erasing? Also, I want my eraser big. Is it still, I guess it still is big. Okay. I just feel like that's kind of small for being a big eraser, but who am I to criticize? We're doing great. Okay. Last little thing for you here today is that you remember how we have said that all objects always accelerate at the same acceleration at g, regardless of their size. So this, you took on blind faith at first, and when I said, hey, if you drop any two objects, they will always hit the ground at the same time, you said, yeah, okay, sounds good. But doesn't it feel wrong to you? Like, doesn't it feel like objects that are heavier should fall faster? Well, today we're going to talk about why that's not true, so that you can see that actually it does make sense that all objects would fall at the exact same speed. Here is a mouse. I feel like it'd just be better if I drew it actually with its little nose like right here. Don't you think so? Oh gosh, okay. Like what if its nose, that's its eye, here's its little nose there. And there's the other eye, like kind of on the other side. Yes, that's a better looking mouse. Okay. Here is an elephant and here is a mouse. Now, here's what we know is that this elephant here has a big weight because it's an elephant. This mouse here has a little weight because it's a mouse. We also know that this elephant has a big mass because it's an elephant. And we know that this little mouse here has a little mass because it's a mouse. Well, take a look. If you wanted to calculate, I'm going to move my picture over here. If you wanted to calculate the acceleration of this elephant, you could calculate the acceleration by doing its weight divided by its mass. And you would have a big weight divided by a big mass. If you wanted to calculate the acceleration of the mouse, you would have a little weight divided by a little mass. Hey, check it out. Something big divided by something big gives you something medium-sized. And something small divided by something small gives you something medium-sized. And so both the mouse and the elephant would have the same acceleration due to gravity. I want you to think about this conceptually. For the elephant, gravity pulls on the elephant harder. But the elephant also has more mass, meaning it has more inertia. So it's harder to accelerate. So gravity pulls on the elephant harder, but the elephant is also a harder thing to accelerate. Gravity pulls on the mouse less hard. But the mouse also has very little mass, meaning it has very little inertia. And so gravity doesn't pull on it as hard, but it has way less inertia, and so it accelerates way easier. So check it out. Gravity pulls harder on the stuff that's harder to accelerate, and it pulls less hard on the stuff that's easier to accelerate. So it pulls harder on the stuff that's hard to accelerate, less hard on the stuff that's easier to accelerate, and everything accelerates together because the stuff that's hard to accelerate gets pulled on very hard, and the stuff that's easy to accelerate gets pulled on not that hard. And so we see that all things fall at the same acceleration, g. And that, ladies and gentlemen, is all for today. Today we talked about three main things. First, we talked about Newton's, well, I don't like that it doesn't have, okay, there you go. First, I don't know why it does that. First, we talked about Newton's second law, and we talked about that as a mathematical equation, which it is. Then, after that, we talked about what net force means and what it means to be in a state of equilibrium. You can calculate the net force on an object by adding and subtracting forces in accordance with their direction. Then, lastly, we talked about weight. We talked about how mass and weight are not the same thing, how we calculate them differently. We talked about how your mass does not vary with where you are, but your weight does vary with where you are. And finally, we talked about why all things accelerate at the same rate. And that, ladies and gentlemen, is just about all of our topics for today. I hope you have a wonderful rest of your day, and I will see you next time. Bye, good people.